Welcome to the chunk on direct ensemble optimization. While standard Bayesian optimization tunes one model at a time, in practice AutoML systems deploy ensembles rather than a single model. The key question that we now ask is, can we actually optimize hyperparameters for the contribution of a single model to an ensemble instead of the standalone score of a model? And the core idea that we're going to discuss here, that is based on a paper by Julian Charles Levesque et al. From 2016, is, can we directly optimize a fixed size ensemble during Bayesian optimization and not only post hoc after Bayesian optimization? Okay, so why do we need another ensemble method? So the standard methods mainly use model produced by a separate training and HPO process. This means we have like two separate processes. One is the AutoML and hyperparameter optimization process. Then we have the separation. And then we have post hoc ensembling, where we actually take the learned models, the library, in order to build an ensemble. And here we actually want to change this and actually steer the hyperparameter itself, search itself towards model that improve the current ensemble. And the question is, can we change the objective in Bayesian optimization such that we search for lambdas that find hyperparameters in the model that, when added to the ensemble, actually lead to the best performance. And the classical Bayesian optimization objective you can see in the top. We want to minimize the validation loss, while the ensemble-aware objective actually wants to minimize the generalization loss when adding a model trained with the hyperparameters to the current ensemble. And E are all the current ensemble members. And as a sanity check, we would then like to figure out whether the empty ensemble actually falls back to Bayesian optimization. How does this look like in practice? We actually do this in a round-robin fashion. We have a history and a fixed size of the ensemble with m slots. At each iteration, we remove one of the models from the ensemble and re-evaluate how adding all of the models in the history would actually perform when added to the current ensemble. So we basically simulate adding them back to the ensemble. And this will then form our training signal on which we train the Gaussian process that we then use for Bayesian optimization. The next step is then similar or actually equal to Bayesian optimization. Using this Gaussian process, we run expected improvement or any other acquisition function in order to obtain a new candidate. We evaluate the candidate, which means we train a machine learning model and make predictions. And then we add it to the ensemble and continue in the next iteration with the next model or the next slot. And on the right-hand side, you can actually see the individual evaluations, which are the crosses. You can see the members in the ensemble. And you can also see the two different objectives. In red, the standard Bayesian optimization objective, and in blue, the ensemble-aware objective. And you can see that the ensemble would next evaluate somewhere around -1, which is the optimum for this acquisition function, while for red, we would actually not have the optimum there, but probably rather at -2. So we can see that the two actually behave rather different. And this also leads to the fact that different ensemble members or ensemble slots can specialize on different regions of the search space. Here we see an illustration of a search with 5 ensemble members. And each of the differently colored lines represents removing one member at a time, and seeing for the whole search space from -5 to 5, how this influences, how this configuration when adding to the ensemble influences the error. And we can see each of these slots has a very different optimum, and that actually we would, for each of these slots, actually like to find different hyperparameters. So different roles or different slots actually specialize in different roles within the ensemble which allows then the optimization procedure to improve them over time and make them really good at their job. Now, one thing to consider here is that using the 0-1 ensemble loss, which is the accuracy, leads to discontinuities and plateaus when using majority voting that are actually hard to model with the Gaussian process. So in practice, we want to have a different loss function that actually takes this into account. And in order to do that, the authors introduced a margin-based loss. So basically, they take the ensemble and they penalize the ensemble by how far the prediction is off, basically off from the margin, so that separates the two classes from each other. And this still picks the best model only, so they actually use the square margin, which actually then gives more weight if we are close to the margin and far away from the decision of 1 or -1. So if we are rather uncertain. And this overcomes the sharp transition boundaries and leads to a smooth objective that can be optimized faithfully. The authors demonstrate the method on 3 different problems, namely optimizing support vector machines, optimizing multiple scikit-learn models jointly, and optimizing convolutional networks on Cypher 10. They find that ensemble optimization significantly outperforms using Bayesian optimization, best model only, and also Bayesian optimization with post-hoc ensembling. And in the simple SVM case, also the ensemble optimization with post-hoc ensembling gives better results than Bayesian optimization and Bayesian optimization with post-hoc ensembling. So this really helps in their setting in practice. And they also find that the ensemble evaluation overhead is modest relative to the training cost, so it's actually affordable to run their procedure. Some practical takeaways for automated machine learning. Post-hoc ensembling is useful, but actually separating ensembling and Bayesian optimization into 2 separate procedures might be harmful. They optimize each new model for marginal gain to the current ensemble and not only the standalone validation score. And they keep the model predictions to enable fast rescoring against evolving ensembles. And unfortunately, one downside is there. The fixed ensemble size M is a design knob that has to be chosen by the user a priori. Thank you very much for watching the ensemble videos.